Hi, I'm Teacher In. We continue our learning of this chapter. This is a number 2 PPT document. In this section, we are going to learn three main equations. They are the first important things in our fluid knowledge, the most useful and the most common. I want you to pay high attention and take it very seriously. These three main equations correspond to mass conservation, energy conservation, and momentum conservation, respectively. These are the three conservation laws in nature. However, in fluid flow, they have exclusive forms. Nevertheless, we should realize that their physical meaning has not changed. The first is continuity equation. For incompressible fluid, speaking in short, the amount that comes is equal to the amount that goes. Under Eulerian method, that is, total upstream flow rate is always equal to total downstream flow rate. That is, for two cross sections in the stream, for example, CS1 and CS2, flow rate Q1 is equal to flow rate Q2, or in another form, V1A1 is equal to V2A2. It's the same with elemental flow. Fluid continuity is a very strong restriction for flow. The speed is inversely proportional to the cross-section area, nothing to do with anything else except the flow rate. Of course, the equation doesn't give us other information such as elevations, pressures, resistances, forces, and etc. Therefore, most of the time, we need other two equations additionally to help solving flow problems. When we meet branch flow, again, what comes in equals what goes out. Of course, this is for volume per unit time, or flow rate. Really, for homogeneous fluid, it represents mass per unit time, because density is constant everywhere. Now pay attention. Continuity equation is just a scalar equation, nothing to do with directions. Now come to the most important equation, energy equation. We will have several steps to derive the final form of it. In step 1, we deal with ideal elemental flow with kinetic energy theorem. You must remember we are talking about steady flow. Take an elemental flow as our analysis object. In time period dt, the flow moves forward in the stream tube from location 1 to 2 to location 1' to 2'. For steady flow, quantities between 1' and 2, it is the overlapping segment, are identical. The external forces include pressure force P1 on upstream section, pressure force P2 on downstream section, pressure force PR on side surface, and gravity G. Then we apply kinetic energy theorem, which says the total work done by the external force is equal to the increment of the kinetic energy of an object in a certain period of time. I have given the expressions of them on this page and the next page. And then we get kinetic energy equation in fluid flow. That's the equation on the bottom. But that's not the end of the story. We should eliminate dV in each term and rearrange the equation. At last, we obtain a beautiful equation which was firstly got by a Swissman, Daniel Bernoulli. I believe you like the looking of Bernoulli's equation because you have recognized the first two terms on both sides of the equation. Yes, you read that right. They are piezometric heads at point 1 and point 2, respectively. They represent potential energy. Now in fluid flow, we also have kinetic energy, which is represented by U squared over 2G in meter. Well, you are able to explain the physical meaning of Bernoulli's equation. Be careful with the working conditions of Bernoulli's equation. So in the picture, we can apply Bernoulli's equation between two red points, but cannot do that between the red and the green. U squared over 2G is called velocity head. The sum of three terms is called the total head, which is total mechanical energy of unit weight. We can use two kinds of tube to measure piezometric head and total head at a point. Then find the velocity head, as shown in picture we see here. Why does the bending tube have a higher head? Because the fluid is rushing right into the tube, and the speed contributed to the head's climb up. By contrast, the vertical tube on the left cannot receive the speed, it just feels the pressure. Bernoulli's equation tells us conservation, the conversion of particles' mechanical energy during their movement without resistance. For example, if we ignore the level difference of a wing near the top side, there are larger velocities due to streamline convergence. Thus, pressures there are lower than the pressures near the flat bottom side. The pressure difference will produce an upward force on the wing, which is called lift force, so it can fly. The picture here shows the geometric meaning of Bernoulli's equation. We can say this is a graphical illustration of Bernoulli's equation. Here's a tube flow running to the right. In the flow, we pick a streamline, the yellow curve in the picture. At point 1 and point 2 on the streamline, we put piezometric head tubes and total head tubes respectively. Pay attention that the two tubes should be installed very closely to ensure they give values for the same point. We can see the total heads are equal. This is result of Bernoulli's equation. So, we can draw a horizontal red line of total heads of all points on this streamline. This red line is called the total head line, or energy grade line. It shows us the total heads along the streamline. According to Bernoulli's equation, it must be horizontal. Similarly, all the piezometric heads can make a line, the green line in the picture, which is called the piezometric head line or hydraulic grade line. The vertical distance between the red line and the green line is velocity head exactly. V2 is smaller than V1 owing to streamline divergence. So, the green line is going upward. Please note that the vertical spacing between the streamline and the piezometric headline is pressure head. Now, let's give a summary. Streamline, piezometric headline, and total headline. These three lines can show us level head Z, pressure head P over gamma, and velocity head V squared over 2g with respect to a certain datum. Now we come to step 2. If the flow is a real flow, not an ideal flow, we must consider resistance or energy loss. So we add a term H prime W 1 to 2 that represents the energy loss of fluid moving from point 1 to point 2. This term is called head loss. So, for real flow, total head line, the red line in the picture, is always downward due to energy loss. But for piezometric headline, the trend of it depends on velocity head, may be upward and may be downward. In the picture, because the flow is a uniform flow, the velocities will not change along the stream. So, the piezometric line, the blue line in the picture, is parallel to the red line. In the last step, step 3, we deal with total flow. Total flow is summation or integration of all element flows inside boundaries. So we have to use integral operation as shown in the equation. Now there are 3 types of integrals in the equation. One for piezometric head, one for velocity head, and one for head loss. In the following, we are going to analyze respectively. At first, we take a look at uniform flow. Here are the features of uniform flow. Number 1, number 2, number 3. To our total flow integral, the most important feature is number 4. The dynamic pressure on uniform flow cross-section has the same distribution as the static pressure. It is the linear distribution as shown in the picture. In other words, on uniform flow cross-section, piezometric head is constant. We can observe the phenomenon in experiment, as shown in the picture. When pressure tubes are connected to different points on same uniform flow cross-section, they have equal head level, or piezometric heads. Well, how about non-uniform flow section? The picture gives the answer. GVF cross-section is similar to uniform flow section, but RVF isn't. So, if GVF sections are chosen for our equation, then the piezometric head integral can become simple, as shown in the page. We don't care about the flow type in between. Pay attention to that calculations of piezometric head are still for the points. Just the values of each point on the same GVF section are equal. Now look at the second type of integral, the integral of velocity head. Unless we know everything about the velocity on cross-section, there's no way to calculate this integral accurately. So we have to take an alternative approach. We use sectional mean velocity instead of point velocity and introduce a coefficient alpha to correct the error, as you see in the top equation here. This coefficient alpha is called kinetic energy correction factor. Its definition and calculation expression is the bottom equation in the page. Alpha is not less than 1. On discharge cross-section, the greater the velocity difference, or The more uneven the velocity distribution, the greater its value. If the velocity is evenly distributed on the section, alpha is equal to 1. Well, in our study, for GVF sections, we take its value to be 1. Last integral is for head loss. We use HW1 to 2 to represent the averaged head loss of unit weight of the flow ridge between the two sections, section 1 and section 2, so we can get rid of the trouble of the integral. Finally, we obtain the energy equation of total flow, as you can see here. We need to pay attention to the 3 points listed here. Number 1, it controls the physical flow relationship between two GVF sections. Number 2, in the equation, Z and P for points, where V for sections, and HW1 to 2 for flow ridge. Number 3, we need a datum for the equation. For the datum, you can select it as you want. Just to make sure it's horizontal and convenient for our calculations. Again, we need to talk about 3 important lines which are based on energy equation of total flow. They are energy grid line or total head line, the green one on the top in the picture, hydraulic grid line or piezometric head line, the red in the middle, and elevation head line. In general tube flow, we usually take the center line of the tube as our selected point. So the elevation head line is the black dotted one in the picture. The picture is showing us the energy relationship of two GVF sections in the stream. It's very clear in the picture, like our analysis of Bernoulli's equation. I won't repeat, though it's very important. Also, we have slopes of each line. Energy slope J of total headline, piezometric slope Jp of piezometric headline, and the tube slope I of the pipe. In particular, the energy slope J is of great importance to the flow. Energy slope means head loss in per unit flow length. Who made it? Yes, resistance did. Therefore, energy slope J can reflect resistances from the tube. The resistance can come from wall roughness, tube narrowness, and even fast running. Yes, that's right. When you run faster, you will feel more tired. So does water. This is an example of headline drawing. Line 1, 2, 3, 4, 5, 6 is the center line of the pipe. The blue zone is a flowing water. I hope you to study it carefully by yourself. You are supposed to be able to draw such headlines independently and answer correctly some questions, such as number 1, what's the flow direction? Number 2, why energy slopes are different? Where does the smallest J happen? Why there? Number 3, why PHL going upward in ridge 2 to 3? Number 4, where's the biggest pressure? How's the flow speed there? Number 5, how to calculate the head loss of ridge 5 to 6. Number 6, etc. Well, if you have any questions about it, don't hesitate to ask me in class. If you have such a problem in the future exam, don't blame me for not reminding you today.